Hello everyone, my name is Ben Saute and I am the Infrared Cameras Product Line Manager here at Telops. In this video today, we're going to be discussing some of the important points related to choosing an infrared camera. The goal here is to provide you with a baseline understanding of infrared camera specifications so you can intelligently choose the system that's going to be most appropriate for your measurement goals. In order to help us put this information into context, I'll also be showing some of Telops products that illustrate high performance over different portions of this capability envelope. Just very quickly, for those who don't know us, Telops has a 25-year history with the development and manufacturing of high-end scientific infrared imaging tools, whether that be broadband high-speed cameras, FTIR-based hyperspectral systems, and everything in between. Our factory is located in Quebec City, where we have some excellent colleagues that are building cameras every day. But we also have offices in the US, France, and China, as well as a global distribution network. This slide shows an overview of our infrared camera product portfolio. And as you can see, we've got a few different lines that are focused on optimizing different aspects of the infrared imaging process. Probably our most popular line is the Fast family, which includes the highest frame rate cameras available on the market and deliver outstanding temporal resolution and stop motion video of super fast events. We also have multispectral systems over here to the right, which are equipped with a fast rotating 8-position filter wheel. This filter wheel can spin during acquisition and is synchronized to the detector acquisition, which allows us to collect images through 8 different bands simultaneously at up to 100 frames per second per band. We've also been working hard on our dynamic range cameras, and we've recently released the HDR M700, which features a brand new camera architecture that allows the user to measure a span of temperatures of up to 900 degrees with a single detector acquisition. This is a big improvement over the approximately 150 degree span that we can achieve with a traditional mid-wave camera and leads to a really dramatic improvement in the overall image quality. Finally, here on the bottom, we have the radio cameras, which are positioned as accessible entry-level systems. The radio family features cooled and uncooled options and is sort of designed to deliver the same scientific quality data that you're used to from other Telops systems at a more affordable, more entry-level price point. So, when we're talking about infrared imaging, one of the first questions that we always get asked is, what spectral band do I need? And the answer to that question is always, it depends. It depends on the nature of your target. It depends on its spectral emission properties. It depends on its temperature properties. For the spectral emission portion of this question, it's important to understand that most real materials show what's called selective spectral emission. That is, they emit infrared radiation in specific portions of the spectrum. Now, if you're doing something like gas detection from a combustion experiment, you might be interested in detecting CO2, for example. CO2 has a characteristic emission in the midwave, and so obviously we want to use a midwave detector to capture that characteristic emission. The key here is that we want to match the spectral band of our camera to the spectral emissions of our target of interest. So the second thing we need to think about here when we're choosing our spectral band is the temperature properties of our target, right? So the Planck law is illustrated here on the top right, and this tells us how much signal we can expect in different bands for a given object temperature. So I'm not going to get too much into the math here, but if you're interested, we're more than willing to get into the weeds with you on this topic offline. But for this presentation here, the important point that I want you to take away is that your object temperature is going to tell you the optimal band for your camera. So on the shortwave side, we're pretty much limited to high temperature objects, shortwave imagery is mainly reflective. So in order to make a calibrated measurement of the thermal emission of an object, that object must be at a high temperature, somewhere around 300 degrees C. So this is what we see on this video here, taken with a Telops S1K camera. We see a lot of detail in the background from the reflected sunlight, and we can also see that flame sort of rising up through the tower with good detail and no saturation. So when we talk about the midwave band, we're primarily looking at emitted thermal radiation, and so the image looks pretty qualitatively different than that shortwave image. Midwave cameras are well suited for measuring objects from ambient to high temperatures and represent sort of the most versatile out of any of the spectral band choices that we have in the infrared. We can see in the image that we have much less detail in the background than we see in the shortwave image, but we also have very nice detail and thermal resolution in the flame portion. So finally, over here on the right, we have this long wave image. Long wave is well suited for lower temperature objects, which I think is kind of well illustrated by the detail that's present in the background of this image. So long wave cameras can be, of course, configured for high temperature measurements, but as you can see here, they're going to be more prone to detector saturation for high temperature objects when you compare that to a shortwave or a midwave camera. So, now that we've got our sort of spectral band selected, we can move on to considering, other factors about our experiment. We can ask ourselves the question, what kind of temporal resolution do I need here? This question leads directly into considering the frame rate capabilities of the camera, where, obviously a higher frame rate is going to give us a more fine temporal resolution. High frame rate imaging allows us to capture sort of stop motion imagery of rapidly moving targets. But of course, this requires us to use a low exposure time in order to minimize the motion blur that results when the target is moving through the field of view during the detector acquisition. So using a short exposure time does have some drawbacks, especially when we want to image a low temperature target. So using a very short detector exposure time to sort of measure a fast moving low temperature target is going to inevitably lead to a low signal level condition and a degraded image quality. So in order to sort of mitigate this deficiency, Telops high-speed cameras utilize large area pixels to maximize signal levels when we use that short exposure time. Additionally, high-speed detectors are typically configured with low well depth pixels, which allows for the collection of sort of sufficient signal levels to make a good image during a short exposure time and a low target temperature condition here. So this table on the right shows some of Telops products that are designed here for high-speed imaging. The Fast M3K is the fastest thermal camera that's available commercially on the market. It's capable of doing measurements at over 3,000 frames per second with a 320 by 256 pixel detector. We also have the M2KUD, which is the fastest 640 by 512, the fastest VGA configuration infrared camera available today. Again, here we achieve 1,500 frames per second in that full window configuration, which is a 50% increase in frame rate over the nearest competition. We also have a shortwave high-speed model in the Fast S1K and a long-wave high-speed model in the Fast V1K. So high-speed imaging, it's really, it's in our DNA. And there's a lot of additional features and functions that I haven't really gone into that kind of help us to optimize these high-speed capabilities. But the bottom line here is that Telops is continually pushing the boundaries of high-speed thermal imaging. And we're really just trying to deliver a very high-quality scientific measurement device, to our users here. So, switching gears here a little bit, maybe the application you're considering doesn't have super strict frame rate requirements. Instead, you want to maximize your ability to resolve small objects or features within that image. If this is the case, you want to be concerned about the spatial resolution performance of your system. Spatial resolution can be described by a few different terms. The detector format tells us the number of pixels that are available in horizontal and vertical directions and influences the total field of view that can be accessed by the camera. We also have the pixel pitch, which tells us the center-to-center distance between adjacent pixels. Pixel pitch is often a primary parameter to consider for spatial resolution, with a smaller pixel pitch generally yielding better spatial resolution than a larger pitch. Like we saw with the high-speed cameras, the pixel pitch will influence the signal levels that we receive from a given temperature target. So while smaller pixels generally will improve our spatial resolution performance, we're going to pay a price by having to use a longer exposure time to ensure that we have good signal levels from our measurement. Finally, we have the field of view, which has two sort of sub-concepts associated with it. The first is instantaneous field of view, which describes the size of the area seen by an individual pixel. And then the second is the total field of view, which is the size of the area that can be seen by the full FPA. Of course, a larger FPA with more pixels will increase our total field of view, which is typically what you see with modern high spatial resolution systems. But both the instantaneous and total fields of view can be modified by the lens choice for a given experiment. So this slide here shows some of the Telops systems that are designed for high spatial resolution and the spatial resolution performance that we can achieve when we use different lenses. So our fast SHD and HD series feature large format detector arrays with small 10 micron pixel pitch, which really allows for very excellent spatial resolution, very nice performance for both close-up and long-range images, everything in between. I don't want to go into all of these numbers here, but I do want to draw your attention to the general trend of spatial resolution that we see with, different lenses. So starting here on the top with the fast M3 SHD line, we can see that as we decrease the focal length of our lens from 200 down to 25 millimeters, we notice two effects. First, the instantaneous field of view significantly increases with a decreasing focal length. And then the second effect that we see is we decrease our focal length, the total field of view significantly increases. So, this is what I mean on the previous slide where I write that, we can modify the field of view parameters based on our lens choice. I also want to mention that we have that these cameras are compatible with microscope lenses. We have options available for a 1x macro lens and a 4x microscope for sort of super close up and small object measurements. Next up here, we need to consider our sensitivity and accuracy requirements. So when we talk about system sensitivity, the most common performance metrics that you're going to come across is noise equivalent temperature difference, or NETD. NETD is often given in units of millikelvin, and it describes the temperature change that's required to yield a signal to noise ratio of 1. This is the technical definition, but I often find it easier to consider NETD as the smallest possible temperature change that can be detected by the system. NETD is directly influenced by pixel well filling, which is a concept that I kind of glossed over a little bit a few slides back. Each pixel in the detector can be considered as an electron storage well with a finite maximum capacity. So when a detector exposure occurs, photoelectrons are generated by the detector and stored in those pixel wells. So the amount of electrons present in the well compared to the maximum well capacity is referred to as the well filling level. So well filling dictates a lot of performance parameters for infrared cameras, including both the sensitivity of the system, its NET, and also the radiometric accuracy. So we generally want over 50% well filling to maximize the NETD and accuracy performance. And in order to do that, we need to make sure that our camera is sort of well configured for our measurement. So one of the critical things we need to examine here is the well depth of the pixels, sometimes called the well capacity. So this parameter tells us how many electrons can fit into our pixel wells. It's not really possible to say definitively, oh, you need a short well depth, you need a large well depth. It's completely dependent on the goals of this measurement. And in this table here on the right, we show some different configurations and their well depths for standard Telops products. So for example, these are some high-speed cameras in the Telops lineup. All of these models have different well depth detectors, and as a result, we'll need to use different exposure times in order to get a good quality image for a target of a given temperature. So this obviously has downstream effects on the frame rate that we're able to achieve. So, it's really important when we're buying an infrared system to carefully consider that trade-off between well depth, the expected NETD, the expected accuracy, and the frame rate that you want to operate the camera at. So another performance aspect we can consider is the requirements around dynamic range. So dynamic range in the broad sense, it's defined as the ratio between the smallest and largest values a measured quantity can assume. So in infrared imaging terms, the dynamic range is going to tell us the span of temperatures that can be measured by a system. So all of Telops systems have built-in tools and functionalities that optimize dynamic range over time and over changing scene conditions, but we always run into a fundamental limit of the in-scene dynamic range or the snapshot dynamic range. That is the span of temperatures that we can measure with a single exposure time. So typically with the mid-wave camera, that snapshot dynamic range is about 150 degrees. Anything outside of that 150 degree span will either be saturated or underexposed. So we've recently launched the HDR M700, which features a completely new detector architecture that allows us to expand that span from 150 degrees all the way out to 900 degrees in a single exposure time. So, maybe this kind of sounds like, oh, that's nice, kind of, nice sort of capability, but really it makes a qualitative difference in imagery, which I think you can see here pretty well in this comparison photo. So with the traditional Telops camera here on the left, we see that a single exposure time gives us saturation in the firework, kind of washes out some of that detail on the cold asphalt background. So that HDR image on the right shows no saturation. We see a lot of that detail in the background preserved, even though it's cold asphalt, and we have that hot target present in the frame. So it's very impressive. I'm quite proud of this camera, and I think that we've had some good interest in this product so far here. So this slide shows some of the benefits of the HDR M700, but really it's kind of just an excuse to play some of these nice videos that we've managed to collect. I'll call your attention in particular to this video here on the top right. This was collected over the summer. Shows a little party we threw for our engineering team to celebrate the delivery of our HDR M700 demo unit. So what you're seeing here is a very strongly contrasted image. With ice cream in a bowl being melted by a blowtorch here on the left. And on the right, we have strawberries flambé, strawberries with some rum lit on fire. So, very hot object over here on the right. So being able to see both this cold and hot objects in the scene at the same time was just something that we weren't able to do before the HDR M700 came along. To me, that detail that you can see in the wood grain on the picnic table is particularly dramatic, kind of really illustrates the value of that high dynamic range imagery that's generated by the HDR. This kind of detail can really improve situational awareness, when our camera is presented with a very highly contrasted scene. It can even eliminate the need for multi-exposure time techniques like super framing that are commonly used to deal with these high contrast scenarios. So we mentioned this briefly when we discussed choosing a spectral band, but it's also important to consider whether your measurement calls for any spectral resolution capabilities. So as we said at the top, most materials are going to selectively emit infrared radiation over discrete portions of the spectrum. And this pattern of emission is often referred to as the material's infrared spectral signature. So this spectral signature is unique, can often be used to monitor for specific materials or even to identify unknown materials if the signature is collected with sufficient spectral resolution. Spectral resolution describes the ability of a measurement system to collect information over discrete and narrow wavebands. So, here at Telops, we implement spectral resolution capability into our infrared camera systems by including a fast rotating 8-position filter wheel. So this is kind of a moderate spectral resolution capability compared to our FTIR-based hyperspectral imaging systems, but it's still capable of providing a spectral discrimination capability with a time-resolved aspect to it. So I'll pause briefly here to mention that my good friend Jean-Philippe Gagnon will be giving a similar presentation in the coming weeks describing our hyperspectral products. So be sure to be on the lookout for that if you're interested in hyperspectral. But back to the multispectral cameras. We've got this 8-position filter wheel that can be populated with spectral or neutral density filters, and it spins during the detector acquisition such that we can get up to 100 frames per second through each channel simultaneously. The filter wheel can be stopped and operated as a single position, which then allows the camera to measure at its full frame rate capabilities. So, it's really like you get two cameras in one. You have this multispectral capability while the filter wheel is spinning, but you can also make a high-speed measurement through any of the 8 filters that are present in your filter wheel. We have a variety of multispectral models, all with different frame rate capabilities, some of which are shown here on this table to the right. A classic application for these multispectral models is in combustion analysis, which you can see in this video here at the bottom. Each of these 8 video streams that you see corresponds with a different filter position, and each of these filter positions is dedicated to monitoring a specific portion of the spectrum corresponding to the spectral emission properties of combustion gases or other objects of interest. Specifying the filters for one of these cameras can be a little tricky, but if you have interest, we have some excellent field application engineers that are very experienced in specifying these sort of balanced filter wheel configurations. High-end scientific imaging, scientific infrared imaging, it's not always a very cheap capability to implement. Of course, in an ideal world, we have all the money, more than enough budget to buy the exact system we need with, all of the accessories and everything. But, unfortunately, we don't seem to be living in that world. We often have to figure out the way to get the best capability within a given budget. So the Radia family is a new line from Telops that is really designed to meet that budget-conscious niche by providing a high-quality scientific imaging capability at an entry-level price point. So the Radia family features cooled and uncooled systems, both with a comprehensive user-swappable lens selection, all in a very low swap packaging, low size, weight, and power package. It's a bit hard to tell from the pictures here, but the Radia cameras really can fit in the palm of your hands. This is a far cry from the, let's call it toaster oven size of a typical science-grade thermal imaging system. But that small footprint, it's of course convenient, but even more than that, it opens up deployment scenarios that were just not possible with some of the larger footprint systems in our catalog. So this table here shows the major parameters and specifications for Radia V60 and Radia M100. Radia V60, this is our first foray into the world of uncooled microbolometer cameras. It's been, an exciting journey learning about this new technology and releasing what we think is a very high quality system at a affordable price. So one of the main things that I'd like to call attention to here is our recently expanded calibration offering for this system. We're very happy to now offer this camera with the high temperature range calibration, which tops out at 1100 degrees, ideal for scientific measurements for combustion analysis, for example, even for more industrial focused applications like quality control or systems inspection efforts. On the cooled side, we have the Radia M100, which features a 640 by 512 pixel detector, the 10 micron pixel pitch. One of the unique things here with the M100 lies in the baseline calibration temperature range. So this camera is very hard to saturate, and as a result, we're able to offer a baseline calibration from 0 to 850 C without using a single neutral density filter. So sort of cut the light that comes into our system. Now, to be clear, this is 0 to 850. This is not 0 to 850 with a single exposure time like we see with the HDR M700, but that 0 to 850 baseline calibration range, it really makes the Radia M100 well suited for high temperature scenes. Both the V60 and the M100 are fully integrated into Telops or VLIR camera control software, delivered from the factory with a radiometric calibration that allows the user to view the collected imagery in units of digital levels, temperature, radiance, or irradiance. These systems are designed to be easy to use, right? So you don't need to have a PhD in imaging science or physics in order to make a high quality measurement. So to conclude, I hope I've given you a good idea of the major experimental and systems capabilities that you need to sort of carefully consider when you're choosing the infrared camera that's right for your measurement. At Telops, our philosophy is to really try and push the limits to make purpose-built systems for different applications. We like to tackle the hard problems. So our focus is on building systems that excel in frame rate or dynamic range or spectral resolution or whatever, not necessarily just all-around systems that might be good for a lot of different applications. This graph here, I think, illustrates well the mix of different capabilities offered throughout our product line and allows you to get a sense of the strengths and weaknesses of the individual families within the product line. So we've got the fast line, which are of course geared towards high frame rate measurements, the fast HD line, which are optimized for spatial resolution, multispectral family, which imparts a moderate yet still time resolved spectral resolution capability. The HDR series, designed for high dynamic range and thermally contrasted scenes. Finally, the entry level radio cameras. So, I hope this presentation has been useful, informative, and I'd like to invite you to contact us by email or through any of our web or social media channels. Thank you very much. See you next time.